The safest way to observe the sun is to use an indirect projection method, in which a pinhole camera, a pair of binoculars, or a telescope focuses and enlarges the image of the sun onto a screen, reducing the brightness to a safe level.
The sun's diameter is 1.4 million kilometers and its distance from the Earth is 150 million kilometers.
1,800 Kelvin, which is 5,527 degrees Celsius.
Hey, what up, peeps? It's your boy Ethan from H3H3. The sun finally came out. It's a beautiful, nice, warm day here in New York City, and I wanted to show you all at home what I'm about. A little peep into the world of EK from H3. Vape Nation!
The visible solar atmosphere consists of three regions: the photosphere, the chromosphere, and the solar corona. Most of the visible light comes from the photosphere. This is the part of the sun we actually see. The chromosphere and the corona also emit white light and can be seen when the light from the photosphere is blocked out. For example, in the solar eclipse. The approximate temperature of the corona is 2 million Kelvin.
Sunspots are darker, cooler areas on the surface of the sun in a region called the photosphere. The photosphere has a temperature of 5,800 degrees Kelvin. Sunspots have temperatures of about 3,800 degrees K. They look dark only in comparison with the brighter and hotter regions of the photosphere around them.
The sun's rotation period varies from 25 days at the equator to 36 days at its poles. The sun's rotation rate decreases as it approaches to the poles.
This is a butterfly diagram showing how the relative numbers and latitudes of sunspots vary with time during the 11-year solar cycle. 3 complete cycles are shown.
The sun's energy is generated by nuclear fusion reactions at its core, converting hydrogen into helium. The sun's core is so hot, its temperature is around 15 million Kelvin, that the hydrogen nuclei protons are able to fuse together to make helium nuclei in a series of reactions called the proton-proton chain.
By studying the sun at different wavelengths of the electromagnetic spectrum, astronomers can build up a much more comprehensive picture of our local star. In recent years, a number of space probes and solar observatories have been launched from Earth, containing scientific instruments designed specifically to study the sun at different wavelengths.
The telescope is fitted with an H-alpha filter. It allows a narrow range of wavelengths either side of 656 nanometers to pass through and blocks the remaining light. The increased contrast allows solar features such as prominences, which are huge clouds of cooler gas in the sun's atmosphere, filaments, which are the same but appearing as dark silhouettes against the brighter photosphere, solar flares, which are sudden releases of energy, sunspots, and the chromosphere to be observed clearly. This photo shows the sun observed through an H-alpha filter. Several features are visible in addition to the silhouetted planet Mercury undergoing a transit across the solar disk, involving sunspots, brighter active regions, prominences, bottom left, and darker filaments. Exceptionally hot regions of the sun emit X-rays. The same picture shows an image of the sun obtained from the X-ray telescope on the joint Japanese-US-UK space probe, Hinondi. The bright regions at the edge of the solar disk reveal the sun's extremely hot corona, and the bright areas on the solar disk are associated with active regions, magnetic loops, where ionized hydrogen flows along curved magnet field lines.
There are two types of solar winds: the slow solar wind, that is a steady stream of charged particles, mainly protons and electrons, but with traces of ions of helium and other elements, flowing outwards in all directions from the sun's corona at speeds of typically 400 kilometers per second. The high temperature of the corona partly explains how these particles gain sufficient kinetic energy to escape the sun's pull of gravity. And then there's the fast solar wind, that is originated from corona holes, cooler regions of the corona close to the sun's magnetic poles, where open magnetic field lines, as opposed to the more familiar closed loops, permit charged particles from the photosphere to escape more easily at speeds as fast as 850 kilometers per second.
Love.